All right, let's look at C19 notes, solving exponential and logs. I think it's best if I just work through these. Don't necessarily pay attention to what the prompts are saying. What's more important is how I'm doing this. So let's just look at number one. All right, 3x plus 1 is equal to 81. All right, so for an exponential, when you're solving an exponential function, it's the idea, the goal is to make it to where the bases are the same, if possible. And then if it's not possible, then that's when we have to take a log on both sides. So kind of knowing your powers is going to come in clutch right now. So on the left, this is 3x plus 1. 81 is 3 to the 4th power. 3 times 3 is 9, times 3 is 27, times 3 is 81. So 3 to the 4th power. Here the bases match. So I really don't care what the bases are at this point. It's the exponents that matter to me. So because the bases match, the exponents are what's important. So this is going to be x plus 1 is equal to 4. Minus 1, minus 1. X is equal to 3. Let's try it again. So I want to get the bases to somehow match. If I can, right? If I can. That's the thing, is if. Here 32 cannot be written as 4 to a power, but 32 can be written as 2 to a power for sure. So 32 is 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So this is 2 to the 5th power. On the left, 4, right, that x over 2, that's the exponent. But 4 can be rewritten as 2 to the 2nd power, right? 2 squared. So 4 is really 2 squared. 32 is really 2 to the 5th. Okay, because the bases match, I'm only looking at the exponents, and we're setting the exponents equal to each other. But these are the parts that I'm setting equal to each other. So on the left, 2 and then x over 2, a power raised to a power is multiplication, right? So this is going to be 2 times x over 2 is equal to 5. The 2's cancel. So x is just equal to 5. All right, that's solving an exponential function, right? When you have the variable in the exponent and the bases can be rewritten. Rewrite the bases. All right, so that's the basic of what we're doing. All right, there's going to be ones that look slightly complicated. All right, there's a typo here. I don't know why this is here, but there needs to be not this box. It's just a dot for multiplication. Okay, let's unpack this. There's a lot of things happening. So, again, notice right now we have base e, negative x squared, base e, and then this fraction. The goal is to have the same base on each side, just like how in number 1 we had base 3, here we had base 2. All right, this is no different. It just looks crazy, but we need to have base e on both sides. So let's do this one piece at a time. So the first thing that I want to do is on the right, get rid of this fraction. That's going to be step 1. So I can change any fraction into a whole number by making the exponent negative. So let me rewrite everything we have so far. Let's make this black. Okay, so I just rewrote the part that I'm not looking at. All right, in red, we have e to the negative 3. That's all we did. All we did to make the fraction not a fraction is change the exponent to a negative. Okay. Now, this middle piece, ex squared. So x and 2 is a power. X is a power, 2 is a power. Power raised to a power, you multiply. So this is going to be e 2 times x is just 2x. I could put x times 2, but it just looks crazy when you do it that way. All right, negative 3, and then e negative x squared. Okay, it's getting better, believe it or not. All right, on the right, the red and the blue, when you have a base, common bases being multiplied, right, e to something times e to something, this is where you add the exponents. Here, we're going to add these two things together. So this is going to be e negative x squared is equal to, I'll do it in red, e 2x minus 3. Right, you're just putting them together. Technically, it's plus negative 3, but you just put them together. And now, look, after some work, they have the same base. And I don't care about the e's anymore. I just set the powers equal to each other. So this is going to be equal to that. Negative x squared is equal to 2x minus 3. Okay. That was the goal, was to set the exponents equal to each other. Okay, now we have a brand new problem. We need to figure out what is x. All right, this is a quadratic. So this is why we learn quadratics first. I'm going to move the negative x squared to the right. So plus x squared plus x squared. So on the left, we have 0. On the right, we have x squared plus 2x minus 3. This is actually not that bad. This one is going to have, right, so however you know how to factor, it doesn't matter the method that you learn. But I come up with two numbers. When I multiply them together, I get negative 3. When I add them together, I get positive 2. So you can pause that and think about it for a second. But this is going to be 3 and 1. Positive 3 and negative 1. When I multiply them, I get negative 3. When I add them, I get positive 2. Okay, so this means inside lies, right? Those aren't the solutions. The solutions are x equals negative 3. Inside lies. And then x equals positive 1. You could just say 1. We need to put positive 1. Okay, there it is. Those are the solutions. All right, I'm gonna do number 4. Okay, this one, again, the goal is to have the same base on each side, and then we don't care about the bases, and we only look at the exponents. So right now, the thing I'm looking at, what I'm thinking is 3, 9, and 27 can all be rewritten as a power of 3. 3 to some power. Okay, 3x squared is equal to 9 to the x power. 9 is really 3 squared. 3 squared, x power. And then this is times 27, which is really 3 cubed. Okay, on the right, common bases, we can add the exponents. So 2x plus 3. So this is going to be 3x squared, 2x plus 3, because we add the exponents. Now, again, same bases, so that means the exponents are equal to each other. So this means that x squared is equal to 2x plus 3. Again, this is a brand new problem now. We're solving a quadratic. Notice how over here I moved the terms around so that x squared is positive. That's just how I do it. So here I'm going to move the 2x and the 3 so that the x squared stays positive. So this is going to be minus 2x minus 3. So x squared minus 2x minus 3, right? Because I got to minus it from both sides, equals 0. Okay. X. What two numbers multiply to make negative 3, but this time add up to negative 2. So it's still 3 and 1. But this time it's going to be negative 3. Oops, why'd I put 3 and 3? It's 3 and 1. Doesn't matter which one, 3 or 1. So it's negative 3, negative 1. Negative 3. Oh, no, wait, that's not true. That's not true at all. That's super false. So it is 3 and 1. So let's see the symbols. Hold on. Like the signs are correct. So negative 3, positive 1. But that's why you always check it. Negative 3 times 1 is negative 3. Negative 3 plus 1 is negative 2. So my solutions are negative 1 and x equals positive 3. So it's kind of opposite of the one that we just did. All right. Moving right along. Okay, so that was exponentials. Now we're getting to solving log equations. So what we just did, the idea was that the bases match. We forget about the bases and we set the exponents equal to each other. All right, this is going to be very, very, very similar with the same idea. The idea is that if the logs match, on each side of the equation, then the arguments must also be equal to each other. And then we'll forget about the logs and set the arguments equal to each other. So here, the logs do match. So the arguments, the parts inside, are going to be 3x minus 1 is equal to 2x plus 4. Right, log base 2 of something, the 3x minus 1, that has to be equal to the other log. It has to. Because there's only a single log on each side, so we don't care about the logs. So this is going to be minus 2x, minus 2x. 3 minus 2 is x, minus 1, plus 1, plus 1. So this is going to be x is equal to 5. So the important thing here is that our answer, when we plug it back in, the inside can't be negative. So when you plug this back in, 3 times 5 is 15. 15 minus 1 is 14. Okay. Plug it in here. 2 times 5 is 10. Plus 4 is 14. Okay, it is a solution. Sometimes it's going to look like a solution, but when you plug it in, you get 0 or a negative number, and then that's just not true. That's just not true, right? The highlighted green part needs to be bigger than 0. Always. Always. So look, we have base 9, log base 9, log base 9. So this means this argument in red is going to be equal to this argument in red. So x squared plus 9x, that has to equal 10. Okay. This is a brand new problem. It's a quadratic. You have to have instincts enough to know that this is a quadratic that we're solving because of the x squared. X squared plus 9x minus 10 is equal to 0. So we have to come up with two numbers that multiply to make negative 10 that add up to positive 9. So this is going to be 10 and 1 for sure. 10 and 1. Plus 10, negative 1. Is that true? 10 times negative 1, negative 10. 10 minus 1 is positive 9. Okay, so these are the factors. The solutions inside lies x equals negative 10 and x equals positive 1. Okay, so this is where we have to make sure that these work. Maybe they both work, maybe they don't, maybe only one. So let's see. When I plug in negative 10 here, I get negative 10 squared is 100 plus negative 10 times 9 is negative 90. Negative 90. So 10 minus 90. Okay, so negative 10 works. If I plug in negative 1, I get, what do I get? I get 1 squared, negative 1. 1 squared is 1 plus 9 times 1 is 9. So also, this one also works. So both of these solutions are true. Both of them are true. Okay. Properties of logs. So same idea, except now we have mad logs everywhere. So we're going to have to condense them down. When we condense them down into one log on each side, then we cancel the logs out basically. So here on the left, it's a plus sign. So that means I have to multiply 2 and 7, right? Because it's a plus, I multiply. Product plus, so log base 3, 2 times 7 is 14. This is equal to log base 3 of x. Oh, that's nice because look, 14 and x. X is equal to 14. And that's because log base 3 is on both sides, right? We don't care about the log base 3s anymore. We're looking at x is equal to 14. Okay. All right, 8. So on the left, we have subtraction. And if you're in my class, you know that subtraction makes a fraction. So this is log base 5, 42 over k. equals log base 5 of 7. All right, this is kind of weird. So we don't care about the logs, and the arguments are what we care about. So here we have 42 over k is equal to 7. All right, solve for k. Multiply both sides times k. Cancel, cancel. Divide both sides by 7. 42 divided by 7 is going to be 6. So k is equal to 6. All right, number 9. Even better. The logs are already on each side. So all I have to do is set their arguments equal to each other. So 4x minus 7 is equal to x plus 5. Minus x, 3x minus 7 is equal to 5. Plus 7, 5 plus 7 is 12. So 3x is equal to 12. Divide both sides by 3. And x is equal to 4. 12 divided by 3 is 4. Okay, let's go to the back. Halfway done. All right, so here we had logs on both sides. That's what we just did. When there's logs everywhere on both sides of the equation. Now, logs are going to be only on one side. So what's going to happen is I was reading what it says. Right. We're going to write it in exponential form. That's going to be the key. So when there's only one log, you convert it to exponential. If you remember the little swirl technique, and then you do what we did on questions 1 and 2, examples 1 and 2. All right, let's get it. So 4 raised to the 3 power. So 4 raised to the 3 power equals, so raised equals, so 4 raised to the 3 power equals 5x minus 1. Notice the log is no more. We don't have a log. 4 to the 3rd power is 64. 5x minus 1. And now we're just solving for x. Plus 1, 65 is equal to 5x. Divide both sides by 5. 65 divided by 5. X is going to equal 13. 5 goes into 6 once. Carry the 1. 5 goes into 15 3 times. So 13. All right, number 11. Here, there's a 8 in front. So the log, we have to isolate it. So that means we have to divide both sides by 8. In this case, that's actually really nice because this is going to be log base 10, right? Because there's no, it's understood that if there's no number, the whole world knows that there's a 10 there. This is equal to 16 divided by 8 is 2. So that's one of our properties, is recognizing when we're in log base 10. It's when there's no number. So since the log is isolated, 10 squared raised to the 2 power equals x. 10 raised to the 2 power equals x. Oh, that's nice because 10 squared is just 100. So x is equal to 100. Let's keep it moving. 12. Okay, isolate the log, divide both sides by 2. It's kind of nice. Log base 3, 2x plus 5 is equal to 4 divided by 2 is 2. Okay, log's all by itself. So solving this, 3 squared equals this, 2x plus 5. 3 squared is 9. Minus 5. Minus 5. 9 take away 5 is 4. Is equal to 2 times something. 2 times something is 4. What do you think this is? X is equal to 2. Okay. Are we there? Are we at the end? Nope. Okay, a more complex log. All right, let's see. What's happening here? There's 2 logs on the left, no logs on the right. So what I'm going to do is I'm going to condense the log down on the left into 1 log. So since it's plus, the arguments, which I'm going to highlight right now, this guy and this guy can be multiplied together. They can be multiplied. So this is going to be log base 10. So I'm not going to write anything. And then 8x times, so we're going to distribute essentially. So this is going to be 8x squared minus 8 times 20. Oh my goodness. 160. 8 times 2 is 16. 0 x. Right here. So those multiply to make that. Is equal to 3. Okay. We know that this is base 10. We know it. So 10 to the 3rd power. Where I want to write this at. Run out of room. 10 to the 3rd power is equal to 8x squared minus 160x. All right, 10 cubed is 1,000. 10 with 3 zeros, or 1 with 3 zeros, is equal to 8x squared minus 160x. Okay, minus 1,000 minus 1,000. This is 0 on the left, big fat 0. Okay, this is kind of unfortunate. I mean, you know, whatever, man. Let's just go for it. So it's a quadratic. So I need to somehow make this smaller. These are all even numbers. These are all even numbers. So I can divide out of 2. Right? If I divide everything by 2, I get 4. Not much better. So 4x squared minus 80, right? Because I'm dividing it by 2, minus 500. All right, do it again. Divide everything by 2. Can I divide it by 4? What if you didn't notice that? Right? Like, I feel like the common person would still be like, oh yeah, just take 2 out. And then divide it by 2 one more time. Yeah, so we could have taken out 4. Like, I actually knew that. This is 20x minus 125. Okay. I mean, slightly better. It's slightly better. So here, let me give me some room up here. This is x squared minus 20x minus 125 equals 0. So really all this log business simplifies down to solving this quadratic. What numbers multiply to make negative 125 that somehow add up to negative 20. This one's not that bad. Right? I say that and you're like, what? It's because 25 times 5? 25 times 5? 25, 50, 75, 100, 125. Yes, this is true. And then one of them has to be negative because they have to add up to a negative number. So the big one has to be negative. So the factors are going to be x minus 25, x plus 5. So the solutions are x equals 25 and x equals negative 5. Are they true, though? That's the question. One of these is garbage. And let me show you why. I'm just going to point out the garbage one. It's usually the negative one, but it's not always the negative one. If I plug in negative 5 right here, 8 times negative 5 is negative 40. And that is just simply not true because log negative 40 cannot be. We cannot have negatives inside. We cannot have negatives inside the log. Right, this is bad. Oh, put it in red. This is bad. So, it's not true. What color do I want to use? This is not true. We could test the other one, but the other one definitely is going to work. Right, if you plug in 25 here, that's a positive number. And plug into the other one, that's also a positive number. But the only solution is x equals 25. Can't have negatives inside, people. Cannot have negatives inside. All right, are we almost done? Okay, so the last combination of solving logarithms and exponentials is when you have exponentials and, for instance, questions 1 and 2 and 3 and 4 actually. So like these first questions was all based on that I could write both bases the same, right? Both bases were the same and then the exponents would match. All right. It is very, very possible that you cannot write the bases the same, right? How do you write 11 as a base 2? You can't. Not evenly, that is. So what happens is when this is the case, this is why logs are so powerful, is because the variable is in the exponent right now. 4 to the x power is equal to 11. I need to take 4 and raise it to something to equal 11. And I don't know what that is. So what we do is we take a log on both sides. Now, the technique is that you use natural log. Why do you use natural log? Because I'm saying to use natural log. You could use any log you want. Any log will work. But I always use natural log. Like, I don't know anyone in their right mind that wouldn't use a natural log. So I'm teaching you to use a natural log. Why do we use the natural log? Because there's a very, very specific property that says if we have a natural log with something that has an exponent, then I can bring the exponent to the front. This is the sole purpose of using logarithms. So we have x times the natural log of 4 is equal to the natural log of 11. So natural log of 4 and natural log of 11, you should not know this, right? This is 1000% calculator work. You gotta reach for a calculator for this. So the idea is that I'm going to divide both sides by the natural log of 4 to isolate the x. So x is equal to whatever the natural log of 11 is divided by the natural log of 4. That's the answer. Now, you could put this into a calculator and get a decimal, but we want an exact answer. So I'm good with this. I'm good with this. I don't know what the key says, but I'm good with this answer. So this is the way it's done. This is the way. Try it again. Number 15. 7 to the 9x power is equal to 15. There's no way to rewrite either of these so that they have the same base. So what I'm going to do is I'm going to take the natural log of both sides. Right? I can do anything I want to an equation so long as I do it to both sides. There's a very special property that says I can bring this down to the front. The whole reason why I'm using natural log is so that 9x is now in front. Natural log of 7, which is some decimal that I really don't care about. This is equal to the natural log of 15. Again, some other decimal that is irrelevant to me right now. Right? It is what it is. So to get x by itself, right? Where's x? Like it kind of got lost in here. Right? X is right here. So I need to isolate this x. That means I need to divide by everything else. So I'm going to divide by 9, and I'm going to divide by natural log of 7 on both sides. Cancel, cancel. So x is equal to the natural log of 15 over 7 times the natural log of 7. Just remember, like I'll remind you one time, the natural log of something is basically log base e. Now, I could have taken the log base whatever of both sides, but the natural log is the quickest and shortest way. And then there's a calculator function for it as well. So that's why we use natural log. That's why I use natural log. This one looks tricky. This one looks like, because 20 is an even number, but 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Right? It passes right by 20. No, there isn't a number that I could raise 2 to off the top of my head that'll give me 20. So what we do is, that is right, we take the natural log of both sides. Because there's a very specific property that says that I can bring the power down in front, right? Like that's super, super useful. So in front, we're going to have x minus 1. Notice my use of parentheses. Natural log of 4. This is equal to the natural log of 20. All right, I need to isolate the x. So this is going to be divide both sides by the natural log of 4. Divide both sides by the natural log of 4. Now, don't get tempted. Do not try to cancel those out. That doesn't work that way. So this is x minus 1, natural log of 20, which is just a number, divided by the natural log of 4. Again, just some number that we could put into the calculator. Isolate the x by adding 1 to both sides. Notice how I put the 1. So x is equal to whatever this is. Now, maybe on the test, you might have a decimal, 24 plus 1. So if I go to Desmos, and we say, what did we say it was? I don't want a function. Divided. So we had natural log. So if you go to functions, find the natural log. So all the way towards the bottom. It's in here. There it is. Natural log of 20 over the natural log of, that's where they have it under calculus. Natural log of 20 divided by the natural log of 4. See, it's only 2.16, blah, blah, blah. Plus 1. Plus 1. 3.16. So that number is 3.16. That would be the approximate answer, right? Okay. So there it is. Good luck. Catch you guys in the next video.